slightly different from the choice of WXE being plus minus 1, because we see that now we need to introduce a defect on the top boundary. So that's actually an indication which one is flux, which one is charge, because in the original 1 plus 1D Ising model, this Hilbert space contains the no charge sector and the charge sector. It actually doesn't contain the flux sector. The flux sector is something different. And in this picture, we see that once we fix the top boundary, we can have no charge sector and the charge sector. But if we want to have the flux sector, we need to do something slightly more dramatic. We need to have a defect on the top boundary.
Ampere constant times Planck charge squared gives you mass length, mass distance, or mass length of dimensions. So what happens when you multiply the Planck dimensions of mass and length, you get one. Duh. Okay. This is something that we assume to see.
But other than that, we see that the flux sector and the charge sector actually has a very large similarity between them. They're just labeled by the plus minus 1 eigenvalue of the horizontal string operator. Okay. And this is going to play a very important role later in our discussion when we talk about dualities, because just a spoiler alert, duality in the sandwich structure will only correspond to a change of the top boundary. It doesn't touch the bottom boundary. It doesn't even touch the bulk.
If we believe this is one, if we believe there's some form of unity here, perhaps we could do something interesting. Perhaps we could try to maybe validate calculations that you can claim are true, and maybe they are, but you would need some method of reference. And I'm sure this is a wrong way of doing it, but I'm trying to be less incorrect.
Okay. So these string operator in the book, they're left invariant. We don't even touch them. They are what they are. And since these kind of things label the symmetry sectors, that's how we can match the symmetry sector before and after the duality transformation. So this will all become more clear once I do talk about duality, but this is just saying that why this symmetry sector labeling being in the book is an important feature that we should keep watching for.
And we literally just, okay, rather than putting the ones, put the units themselves there. Or the units occasionally are defined by some of the other terms, and there's a lot of history there. It's quite fascinating. Okay, so the whole claim is, all right, if we assume that's a 1 and we put in the units, we can get this dimensionless number here. All right, so I put it in that way, gives me a really small number. Okay, so I put it in the numerator, the kilogram meters, divide by that thingy we're talking about. All right, it gives me a really big number. All right, so we get that really small number. Okay, really small, because it's negative 43, really big. All right, so we assume this is 1. All right, so we plug the numbers in. And we assume coming together, we get that kind of unification thing. Because like, all right, I toss in the Planck length, it's like, why am I getting the Planck mass or something like, because these are 1s. Cool. And we have high confidence in these to so many significant digits. All right, so what happens when we get this? We get this number right here. That's a lot of zeros, my friend. How many zeros is it? That's approximately 10 zeros. Shout out to the folks at Wolfram Alpha, because I'm like, the speed of light, it's like they got like 9 significant digits. H bar, they had 12, they cut it off because the error was kind of large, but it's like, you got that, you got the electric constant and everything and stuff in there. It's like, bravo, they got 10 significant digits. That's about as accurate as you can get for, I think, the data that you put in there. Okay. So, if we believe this to be true, if we believe this to be a 1 type of thing with this construction, what would happen if we took some calculated terms, let's say the ones that did geometrically by calculating, taking the numbers we had and then solving for x when setting it to e and then raising it to the... And again, it's a claim. It requires a thoroughly constructed model to help gain confidence in. Is there another way to check? I don't know. But I did that stuff anyway with the calculated values that had. So basically, when we put this in here, and again, we get our deviation. What is it? 1, 2, 3, 4, 5, 6. Okay, 7. On the 7th digit here. All right, we get that deviation because that's about. There's a lot of stories we can talk about. We'll talk about them another time. But okay, so we got this thing in here. So we got basically this number. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 9 digits there. It gave us like 10 digits of accuracy, so it seems to be very precise. Okay. So we did that guy. Oh, all right. So we get some more digits here. We got 1, 2, 3, 4, 5, 6. It does deviate around 7. Very small, but it does deviate. All right, so what is it? 7, 8, 9, 10, 11, 12, 13, 14, 15. I made this kind there. All right, so we're just doing the same thing. We're just doing the calculated values. All right, what do we get? That's a good deal of zeros, my friends. How many zeros? According to my calculations, or Wolfram Alpha's calculations, 16. So, now, what does this all mean? I don't know. It's... The whole claim was, maybe it's a way to check for some form of what people may call a unity. I'm saying that in quotations, because unity does mean different things depending on the context. But is there a point of what we would, at least within our realm of what we can measure these stuff and things, be a point of union? I don't know.